My name is Jay Garland. My background is a technical one. I've worked with NASA for 25 years on this kind of water recycling processes. This is the second year of the design challenge. No matter where astronauts go, clean water will always be needed. The title of the talk is, training for teachers interested in the waste limitation management and recycling design challenge. So what is WLMR? It's designed to be both a series of classroom science activities and a design contest with prizes. So in terms of a classroom activity, what you'll see in the educator's guide is that there's background information on things like the moon, on the chemical nature of water, the hydrological cycle, different approaches that are used for water recycling, and then some more specific information on ISS. And then finally, we talk about what is in wastewater. And what we've also done as a classroom activity is that there's separate activities to demonstrate these different processes. So you'll see laboratory exercises for things like filtration and distillation and separation by force. All these things are in the book, and you can go over these things with your students to give them some background. And for example, one of the projects is on distillation. And distillation is one means of cleaning water. So we go through with this it's kind of a step-by-step process on how you could do a distillation experiment in the classroom. And then we actually talk about this specific nature of space conditions and how that might influence the processes. For example, if you're distilling something where you're boiling it, clearly the pressure that the water is exposed to has a big effect on what temperature it boils at. So that has relevance to space applications, but it also is useful for teaching your students about the interaction between pressure and temperature and boiling point. So let's talk now about the second aspect, WLMR as a design challenge. And then the first thing they're going to do, and this is one of the activities in the back of the teacher's guide, is create what we'd call an analog wastewater. Using common household chemicals. One thing we talk about in the teacher's guide is personal protection equipment for the students. So I put on my safety glasses when I deal with these chemicals. First thing is Johnson's baby shampoo, which is just to simulate what would be in what we call hygiene wastewater. So if people are washing their selves or washing other things, you generate what's called a hygiene wastewater. And the major contaminant in that wastewater is the surfactants or soaps that you use in the cleaning process. And we, in the recipe, call out specifically to use Johnson's baby shampoo, not because we are recommending this particular brand, but we want to use a standard for all the students. The major stream on ISS right now is urine. And what is in urine? Well, one of the major ingredients is nitrogen in the form of ammonia. So we recommend using an ammonia cleaner that the students add to water. The other thing that's in urine is bicarbonate and salt, like sodium and chloride. So the ingredient calls for regular table salt for the students to add, and just baking soda. And there's certain defined amounts they add. Then finally, the other wastewater stream that's in a closed spacecraft is when the astronauts breathe and also perspire, there's evaporation of water, and then that's condensed out of the air, and that's what we call atmospheric condensate. That water is pretty clean, but it does contain some what we call volatile organic compounds, things like alcohols and things like vinegar. So we use just regular white vinegar as a simulant of what would be in that wastewater. So we combine them all together, and the recipe the students will generate is something that has all these 5 chemicals together. But again, things that are very commonly used in the household, not particularly harmful. Students will use a standard set of analytical tools to measure the water quality. So what they have to do is they're going to design a system to clean the water, but we've given them a very standard set of tools to say, okay, this is the quality of the water to begin with, and this is the quality of the water after their treatment. And that's one of the ways we're going to judge how effective they are in their design challenge. First is the pH of the water, which you can use with pH test strips, which are very easily obtained at aquarium stores or pet stores or even pool stores. Also, an ammonia test kit to see how effective they have been at getting rid of that ammonia that they added to the wastewater. And to measure salt concentration, the way that we have the students do that is using what's called a conductivity meter. I have one here. There's various different brands of a conductivity meter. But the basic idea is that it measures how readily the water conducts electricity, and that's a function of how many dissolved ions are in the water. So if there's more salt, it'll have higher conductivity. If you get rid of the salt, it'll have very low conductivity. The final test that we have them do is related to trying to measure the surfactant, which is the molecules that are used to clean things. And this is the baby shampoo. I'm going to put a little bit of the baby shampoo in there, then dilute it. This simulates what's in their normal full-strength wastewater. So if you look at that water, it's already foamed, because that's part of the process of their surfactant. It's a surface active agent. It produces this kind of foam. So the students, what they'll do is they'll take their wastewater and shake it, and you can see that you very readily get a very foamy layer. So what they'll do is they'll measure that layer, and they'll create a range of water with surfactant in it, different concentrations, and create their own standard curve in essence. So as you have lower and lower amounts of surfactant, you'll have less and less foam. So that when the students then treat their water, and at the end of their process they do a shake test on it, they'll then look at the layer of the foam, the depth of the foam, and that'll tell them how much of that surfactant is left and how effective they've been at removing it. Pretty simple test, and they're standard among all the classrooms. We do not want some classrooms doing advanced testing. We want to see the same results, the same tests from all the students. Because the key here is not necessarily the results, but it's the creativity of the students in developing a process for recycling the water. Our focus here is giving the students some technical knowledge, a little bit of technical knowledge about what's in wastewater, how you'd remove it. But what we really want to emphasize is creative, integrated thinking amongst that team. Because this wastewater analog that we've created is simple, it's relatively easy to make, but trust me, it's complex. And there's no single magic bullet for treating it. That's very easy. So how do we recommend the students attack this problem? Well, first we've emphasized the team concept. In the teacher's guide, we talk about recommended roles that the different team members may have. Engineer, scientist, the logistics person, but they can do it any way they want to. But the point is that we do want to see a team effort. And my recommendation is, the first thing they need to do is develop a design. And they need to formulate some basis for their design. They have to develop a rationale for why they use this or why they modified some other existing approach. We want to see where their idea came from. And then we want them to see that they kind of brainstormed ideas and thought about new approaches and maybe the limitations of the existing approach. After that, then they can start to assemble and test and evaluate. And then reassemble, retest, and reevaluate. The best teams from last year were the ones that really went through this in an iterative process, which is the way that science works. You really need to do some experiments, see how it works, and then redo it based on what those results were. We will assess the initial entries based on 3 criteria. One is the effectiveness of the system for improving water quality. So this is going to be the test results. We also want them to evaluate the sustainability of the design. And this means that we want to see that the students try to quantify the cost of their system. Because if they're trying to recycle the water, but they're using large amounts of energy or some other consumable to do that, then it's not a true benefit. And then finally, we want creativity. We want to see that the students did multiple tests and adjusted their design based on the results, really using the scientific process. And then finally, the 20 finalists, in addition to those criteria, the 20 finalists will be assessed on the quality of their presentations. We're not looking for technology. We're looking for those new minds. That's the real product of this effort, is not what they're going to produce, but the students themselves. So I certainly hope that this would lead these students down a career path where they would be producing products and research findings that NASA and the country could use.